Hello everyone and welcome to this lecture. We're going to talk about the Poisson process here. So let's get into this. In this lecture we'll be talking about Poisson process and the relationship between Poisson and exponential. And this module is going to cover these two random variables and their relationships that they have. Referring to the textbook sections, you can look at these sections for more information on the textbook. And later I'll share with you Poisson process in a nutshell, which is a PDF document, and you'll be able to study more in this subject. So in general, we have stochastic processes, and stochastic, this word means uncertain, right? Or random, basically. We're talking about some uncertain processes and random processes, and it includes a family of random variables that describes the evolution of a process over time. So whenever we have a process that changes over time, arrivals of customers to a store, arrivals of patients to a hospital, arrival processes tend to be modeled quite often as stochastic processes. And the way that we show the state of the process at any time is with x of t, where t is the time. And so that basically shows the state of the process at time t. Number of customers in the store in 2 hours, or number of patients in the hospital at 3 o'clock. So that's x of t. So this t, or time, can be a countable set where you basically discretize the time, such as years, 2013, 2014. It's kind of a discretizing the time, or it can be an interval of the real line, basically a continuous time. Which is, for the most part, time is continuous, and we'll be dealing with the continuous time situation. As an example, you can think of size of a population at time t. That's a stochastic random variable. Or distance a particle moves in time t. So in this case, for example, if t is 2013, that is a discrete time. But if t is, let's say, in 2 hours, that is a continuous time. So what we're going to be focusing on in this module is a pretty elementary or basic stochastic process known as Poisson process, which is a very common process to model evolution of a process over time. So let's get into the details of Poisson process, which is going to be the main focus here. First of all, it's a continuous time stochastic process. So the time interval is continuous. And it is very useful to monitor occurrence of some event of interest. You can think of arrivals, arrivals of customers, right? Or, received calls. So if you think about a customer service center that receives calls, you can model that as a Poisson process. That process of arrival can be modeled as a Poisson process. Received call, for example, in a morning shift, right? A very critical element or parameter of Poisson process is the average rate, right? What is the average rate of calls that coming into the customer service center in an hour? What is the average rate of arrivals of customers to the store? So that average rate is very critical. And does not change over time. That's an average rate. Average rate also is denoted by lambda. So lambda, this is how you read it, is a very critical parameter of Poisson process. The random variable that we're dealing with here is n of t. And n of t is, you can think of number of times the event occurs in time 0 to t. So you can think of a horizon that represents time, and this is time 0, and this is some time, let's say 30 minutes, 2 hours, 10 years, whatever. And the number of arrivals or number of times that any event of interest happens in that period of time is n of t. And obviously that is going to be random, right? So if you're talking about number of customers arrivals in 2 hours, this t is going to be 2 hours, and this n of t is going to be random for the most part, right? You don't know how many customers are going to arrive. So we're going to study this random variable in Poisson process. Obviously, if t is 0, the number of arrivals in 0 time is going to be 0, right? Obviously. Also, the increment of time is independent. So what happens in an interval of time does not depend on any other non-overlapping interval of time. So what happens in between 1 p.m. and 3 p.m. does not impact what happens at 4 to 6 p.m. So we talked about this notion of independence. So whenever the time periods are non-overlapping, these random variables are independent from each other. So if you have number of arrivals in time t plus s, and you subtract the number of arrivals in period of time equals to s, what is remained is the number of arrivals in time t, right? Number of occurrences. I usually say arrivals because a lot of times we use that for modeling arrival processes, but you can think of any occurrence in interval of length t. So you can think of, again, a time horizon here where we have 0 and then you have time t, and then here you have t plus s. This is a random variable, number of occurrences in time t, and this is number of arrivals or occurrences in time s. Obviously this is n of t plus s. So this relationship between n of t plus s, n of t, and n of s is true for any s and any t. So generally speaking. So let's talk about let's start talking about how to calculate probabilities associated with this random variable, right? If you want to know what is the probability that I see 5 customers coming into a store in 2 hours, how are you going to calculate that probability? So let's take an example here. The number of customers arrive to a bank in 1 hour. Well, obviously this 1 hour is giving you the t, right? So t is 1 hour. Basically your random variable is going to be n of t, which is in this case is going to be n1, right? And this n1 or x is a Poisson random variable with some average, with some mean of alpha. So alpha is the only parameter for any Poisson random variable, and alpha is equal to lambda t. So a lot of time in textbooks you see alpha, that alpha is equal to lambda t. So therefore the way you notate the random variable is x follows a Poisson with mean of alpha. but you know that alpha is equal to lambda t, and your random variable is n of t. So alpha is equal to lambda t, and just to remind you, this lambda is the arrival rate, right? 8 customers per hour, 2 patients per day. And t is the time. And that is the only parameter for Poisson process. Let's take one example. Let's say lambda is equal to 1, which is basically number of customers per that arrive in an hour, right? So it's a hourly average rate of arrival, and your random variable is n60. So n60 here is your random variable. It is random. So it's the number of customers that arrive in 60 hours, right? So we're talking in terms of hours. Everything is hours. That is a Poisson process or Poisson random variable with an average of lambda t. So that lambda t is 1 times 60, right? So 60 is the parameter of this Poisson random variable. So I know at this stage it's still very notional, but we're getting into some more details here in a second. So just remember that the alpha is equal to lambda t. Lambda is the arrival rate, and t is the time, which basically can be any number, depends on your random variable. Now, if this Poisson random variable is the number of arrivals within a time frame, right? You have n of 20 minutes or n of 30 hours. And all of them are number of arrivals. So number of arrivals is discrete, right? Because you cannot have 1.5 arrivals or 30.6 arrivals. It's a discrete and has a range between 0 all the way to infinity. So it is a discrete random variable. So when you think about discrete random variables versus continuous, Poisson random variable is discrete because the number of arrivals is always going to be discrete. How do we calculate probabilities of Poisson random variable? Here's the PMF function. So the PMF function, it's used to calculate probabilities. In this case, this is your random variable. It can be n of t, any t. And this is the outcome that you're interested to calculate the probability for. So it's basically a constant. It's a number. Let's say you're calculating probability of n60 equals to 3 arrivals in 60 hours, let's say. So the way you calculate that is with this formula, where again your alpha is lambda t, and that's all you need to know basically. So you know that for any discrete random variable we have a PMF, we also have the CDF. CDF is simply the summation over the PMF function. So if you think about the CDF function here is a summation over PMF where you have the P of x equals j changes from 0 to the x. So you have to add the PMF or sum over the range from 0 to x over the PMF function as it's happening here. The expected value average of Poisson process is lambda t, as well as its variance also is lambda t. So these are some basics about Poisson process and what it represents. We're going to look at some examples in the next video.